Today we're going to make a Bose-Einstein condensate at home, which is a Nobel Prize experiment, and now you can do it at home.
That's right. So we have set up a ultra-cold atom research lab that is available to be controlled via the cloud through our web app or through our Python API. What I'm going to do is show you how easy it is to recreate the 2001 Nobel winning prize in creating a Bose-Einstein condensate. Anyone can go to oqtant.infleqtion.com and sign up and register for a free account, and you can do this for free. So what I'm going to do is I'm going to have you create your own custom Bose-Einstein condensate.
Awesome, let's go.
Which sides here?
Yes, so this is very close to my heart. I don't know if you know the story, but actually I did my undergrad in neutral atom quantum memories.
Oh,
and so
perfect.
This is like going back to my OG days. I didn't have that because it's like $2 to $5 million to do this experiment.
Yep.
And I don't have $2 to $5 million.
Yep.
As it turns out, most people don't. And now you can do it for free.
And you know, that's exactly it. There's only a select few that have had the privilege to be able to research with ultra-cold atoms and Bose-Einstein condensate. This is actually perfect because there's only a limited few people who can really work with Bose-Einstein condensates just for that reason. It's not easy, it's expensive, and it takes a lot to maintain. We're trying to eliminate all of that so more people can get into this field. Anyone can create an account, have an account ready for you.
Okay.
And for free is you start by clicking on My Jobs. And here, if you've already have an existing account, you will see existing data that you've run either through the web app or through the Python. And we will start and have you generate a Bose-Einstein condensate. Click on the BEC generator. And really, there's a lot of stages that happens when you cool atoms and get it into a BEC or a condensate. Most of those stages are not really fun and left it to the most important stage and the most fun stage. The last stage, we have atoms that are near a chip, and that chip sends RF frequencies. So that last stage will send RF signals to the atoms, and those signals will match to certain energy levels of atoms that you want to remove from the cloud of atoms to create that condensate. So the level of RF frequencies is essentially telling the system, I want to remove atoms of a certain energy, of a certain temperature.
Okay.
And it's always nice to our default is to be nice about it and be gentle to create a beautiful BEC. But we allow you to customize it. So you can either enter values or drag the little labels here and to adjust your frequencies. And as you're doing this, I'll explain that it's essentially a 5-stage steps in over a 1.6-second period. And so that's what those 5 steps are. It's just saying step 1, move at this energy level, and then start getting colder and colder. Once you're happy with those energy levels that you are going to remove, then we go to power. You're choosing what energy of atoms to remove, and then how powerful you want to remove them. The more power you apply, the more atoms of that energy that you're going to remove. But in the end, your BEC is going to have less atoms. So there's a balance there, and depending on what you're trying to go for, you can adjust these values accordingly. Once again, we always set some default parameters to get a beautiful BEC, and then you can play from there and understand the impact of those adjustments.
Perfect. Well, we want to make the most beautiful BEC, so I'm going to leave the values alone so far.
Okay, customize your BEC by giving it a name. All right. So after a BEC is created in that trap, the way that you measure the characteristics of it is you have to release it from the trap and take a photo of it. Depending on the time that you take that photo, it will start to expand, and you can have more accurate measurements of the BEC, but also see how it becomes a little more in the classical nature, and those thermal atoms, will kind of spread out. So you can choose between about 2 milliseconds to 20 milliseconds to when you want to take that snapshot. Once again, we've set sort of a default in the middle. The closer you are, the more mixed atoms you'll have in that cloud. The further, the more thermal it will be. So you can choose whatever time.
Sounds good. Oh, and there's a little tooltip, time of flight, that explains a lot of this here.
There you go. Yeah, so if you ever have questions about what am I doing here, we have these little tooltips everywhere, and you can click on it. So it's a great find. So if you're happy with these settings, then you can hit Submit Job. And that took, without us talking, it probably took, 30 seconds to a minute to make those decisions.
Yeah, so this is a big thing, right? So a lot of people say like, oh, it's not actually running, it's a simulator. This is actually going to their equipment in Colorado.
Yes.
So it's right there. So, you might have a wait time if someone is using the machine.
Yeah.
but it's actually going to real hardware and you're actually creating quantum matter.
Yeah, real atoms, real hardware, no simulations here. What I'm going to explain to you is what actually happens when you see your job that says running. And this is how we create a Bose-Einstein condensate in Oqtant. So essentially it starts with this double high vacuum glass cells, and we have rubidium atoms that are ejected into the first cell. We use 4 laser beams to cool down that cell, and then 1 to eject it up into the top cell. This cell is surrounded by magnetic coils, and we generate a MOT, which is a magneto-optical trap. We use that MOT and cool it further until we move it to that chip. And this is the chip that I explained it sends RF signals to the atom cloud, and it sloughs off those thermal atoms to the degree then all of the rest of the atoms form a condensate. So now you have that condensate at the trap and you release it. As it drops, it will start to expand and the more thermal atoms will leave that condensate. And this is the point that we took the snapshot image.
Very cool. What can I actually do with a BEC? What are the applications of it?
The special thing about a BEC is that you've taken thousands and thousands of atoms and have condensate them into a point where they're all at the same ground state. And what that means is that they're all behaving the same. And normally when you're studying or you want to work with atoms or study quantum effects, it's really hard to take an image of a single atom. But what you've done is that you've taken the thousands of atoms and they form into essentially a super atom, a macroscopic, very large atom that you can then image and start taking measurements from. So now with that capability in your hand, you can really start to leverage all of these quantum effects such as tunneling, superfluidity, atom interference, and start to manipulate it and demonstrate different techniques, including sensing. So sensing is one of the areas that we are especially focusing on because with these ultra cold atoms, they can be a lot more sensitive than say using cold or vapor atoms. And so this is an area where we can produce more precise sensors for measurements in acceleration, gravity, and also rotation. So these are some of the applications that we are going into and that can be applied. And what the cool thing is that now that we are making this capability available to everyone, there are probably applications out there that we haven't even imagined. And we can have people in agriculture and in energy and medicine start thinking about ultra cold atoms using quantum in their fields to unlock new use cases.
Yeah, that's been the really cool thing that I've seen all around the quantum space, right? It's just, it used to be trapped in the lab and the domain experts don't have access to it. It's just a bunch of physicists. And now we're actually able to put this technology in the hands of people that will actually use it.
Yes.
So, I don't have the domain expertise in agriculture and, I'm so excited to see what people will do with it.
Yeah. And not only that, but we need to get this science and this technology into the classroom. And really it can easily be starting at the elementary age when they start learning about solid, liquid, gas. Why not talk about plasma and Bose-Einstein condensate?
Yeah, because Bose-Einstein condensate is the 5th state of matter.
That's right. That's right. Think about 4th grade, 5th grade, they're introduced to this field and it can capture more students. And one thing that we have in the STEM field is that we lose a lot of interest amongst, different demographics. And if we capture that interest at their early stage, this makes it accessible for them as they move along. And so we're going to encourage more students to go into this field, study it, and start developing new technologies in the future. Now, it was pending, it was put into a queue, then got out of that queue, and then it was running. And that means that your BEC was being made. And now it's complete. So you can click on the job, and an image of your Bose-Einstein condensate is right here. What this is essentially we shine laser light onto the condensate at the time of choice after it's dropped from the trap, and we can measure the optical density, or essentially like the shadow that's created. And from that image, we can extract out information about the BEC. and we provide that towards the top. So here are some characteristics of the BEC. The number of atoms in the condensate, so you have about 13,000 atoms, and the temperature, and this is one of the coldest ones I've seen so far today. 66 nanokelvin. So we're talking about 66 billionth of a degree to absolute zero. So just a few minutes ago, you created the coldest place probably on Earth.
People ask me about space as well, and you all have actually put a BEC in space at Infleqtion. But one of the coolest things here is you're looking at this 66 nanokelvin, and space is actually about 4 degrees Kelvin. So this is actually way colder than space.
Yeah, exactly. And most people think outer space is the coldest. And like what you said is that we have a BEC type. There is a machine that's on the space station, so they create the coldest space in the universe because they can get to picokelvin levels.
Wow, really?
Yeah.
Oh, amazing.
Yes. So this is really the first step when it gets into research and development using ultra cold atoms. We have other tools available, which include projecting laser beams onto the condensate to manipulate them. And then through our Python API, there's a number of demonstration notebooks that people can recreate quantum phenomena that they learned in these textbooks.
Very cool. Now, tell me a little bit about you.
So I've been with Infleqtion for about 2.5 years now. My background is actually in biomedical optics. So I've worked in the optics and photonics industry for about 13 years and found that the quantum was an exciting space to go into. So I joined Infleqtion, and I have been leading this program pretty much almost from its inception to now when we've launched it just about 2 days ago.
Yeah, so congrats. That was a big announcement 2 days ago. We're at Q2B, which is one of the bigger quantum tech conferences. And it's so fun to see what everyone is doing every year. It's been running for about 7 years now, and the quantum industry is still a little bit small, but coming back here every year is really exciting because you see old friends, you see what we've done over the last year, all the different companies, all the releases, and it's just a really good time. So check out Oqtant and Infleqtion, and you can go and run your own BEC.
And one last thing is, I don't have a Nobel Prize for you, but I do have a button that says that you made quantum matter. So congratulations.
Artificial intelligence is the hottest new thing in technology right now, but my next guest says there's something else we should be paying attention to: quantum computing.